But the difficulty really is psychological and exists in the perpetual torment that results from your saying to yourself, but how can it be like that? Which is a reflection of an uncontrolled but utterly vain desire to see it in terms of something familiar. I will not describe it in terms of an analogy with something familiar. I will simply describe it. There was a time when the newspaper said that only 12 men understood the theory of relativity. I do not believe there was ever such a time. There might have been a time when only one guy did, because he was the only guy who caught on before he wrote his paper. But after people read the paper, a lot of people understood the theory of relativity in some way or another, certainly more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics. So do not take the lecture too seriously, feeling that you really have to understand in terms of some model what I am going to describe. Just relax and enjoy it. I am going to tell you what nature behaves like. If you will simply admit that maybe she does behave like this, you will find her a delightful and entrancing thing. Do not keep saying to yourself, if you can possibly avoid it, but how can it be like that? Because you will go down the drain into a blind alley from which nobody has yet escaped. Nobody knows how it can be like that.
That's awesome.
I love that. Just accept it.
Yeah.
Don't ask how can that be the way it is. And I love that he says no one understands quantum mechanics. Okay, so then, let me describe to you the behavior of electrons or photons in their typical quantum mechanical way. I am going to do this by a mixture of analogy and contrast. If I made it pure analogy, we would fail. It must be by analogy and contrast with things which are familiar to you. So I make it by analogy and contrast, first to the behavior of particles, for which I will use bullets, and second to the behavior of waves, for which I will use water waves. What I am going to do is invent a particular experiment and first tell you what the situation would be in that experiment using particles, and then what you would expect to happen if waves were involved, and finally what happens when there are actual electrons or photons in the system. I will take just this one experiment, which has been designed to contain all of the mystery of quantum mechanics, to put you up against the paradoxes and mysteries and peculiarities of nature 100%. Any other situation in quantum mechanics, it turns out, can always be explained by saying, you remember the case of the experiment with the two holes? It's the same thing. I'm going to tell you about the experiment with the two holes. It does contain the general mystery. I am avoiding nothing. I am bearing nature in her most elegant and difficult form. And so then there's a long explanation, which I'm not going to read, but it's basically the double slit
experiment.
Yeah. I mean, the way he explains it obviously is very cool, but you just can't do it in audio. But yeah, he starts out with, let's look at what happens if you do this with lumps, like bullets. And then he says, this is what happens if you do it with waves, and he shows you how there's an interference, constructive and destructive. And then he just goes on to basically say that the electrons or photons appear to show up in lumps, but they also display the wave patterns of interference, unless you try to look at them with other light, in which case you destroy the interference, and then they just look like bullets after that.
Yeah. They look like particles after that.
Yeah. And then he talks about let's weaken the amount of light, because he's saying you put a very strong light in there, and as the electron passes through the light, it will affect it, and you can see how the light's being affected, and that allows you to see the electron. But obviously that's messing with the electron. So he talks about weakening the light, and all that results in is you missing most of the electrons. So then you don't see the ones that you're interested in, because they're the ones doing the thing that you can't see. And the ones that you do see don't do the thing that you're interested in because you hit them with the light.
Yeah. It's great. I love it. So this is the thing I got from this, because I've listened to a bunch of his audiobooks, and him talking about this in various lectures, or even in his courses. And the thing I got from it is just, it's like, we've talked about it before, but the basic idea is that in order for us to make an observation, there has to be an interaction.
Yeah.
It's like you can't sense something like this. The act of sensing something is really literally reaching out and touching it.
Right.
With some something.
Yeah.
So when the thing is in a void and it's not having any interactions, it behaves one way. We can't know what that way is.
Yeah.
And the only way we will be able to figure it out is by inference.
Yeah.
Right? So there can be no direct observation of that, at least at this point.
Right.
With whatever with the tools that we have. And I'm assuming
it has to interact with something for you to see it. I mean,
right.
Yes.
And so it's kind of, it goes, one of the analogies I like is that the idea that you can't see a blade of grass, really. You're not really seeing what the blade of grass is or what it looks like, right? In terms of light.
Yeah.
Because you're only seeing the light that's being reflected off of it.
Yeah.
So like what it is absorbing, it's almost as though it is more like the light that it absorbs.
Right.
Because that is the light that it's in tune with.
Yeah. Yeah,
and
what you're seeing is the light it rejects.
It's the light that is completely out of tune with, and it's just bouncing off the thing. It's like, nope, you don't fit. Mm-hmm. And so then we're like, blade of grass. No. That's what it isn't.
Right.
So it's, you know what I mean?
Yeah.
It's kind of a cool analogy to me, but.
Yeah. But he has a couple of other interesting ways to talk about this double slit thing where he's basically showing you the curves.
Yes.
Of what happens, and he sort of shows you like, here's what the curve looks like if it's bullets, right? And then here's what the curve looks like if it's waves. If you do the experiment where you're shooting bullets at the plate and they're going through the slits, and then you're measuring what's happening after they pass through the slits on the other side, then you get this particular kind of curve. And then you set up the experiment again where you're making waves.
The curve is when you're graphing it out, like
right?
When you're yeah.
Yeah, I'm sorry. Yeah, you're graphing out the responses that you're getting on the detector plate at the other end, on the other side of the double slits. Then you do the same thing with water. You've got something that's pulsing in the water, so it's making waves, and it's passing through, and then those waves have to go through two holes, and then the waves that come through those
side-by-side holes.
Right, and then those two holes, he first says it like, let's make waves in a pool, and then you've got some bar that's got two holes cut in it so that the waves can pass through. And then you've got a detector at the other end of that. And he shows what happens if when you move the detector up and down or back and forth, farther and closer, and how these two things will change depending on what they are. But what's interesting is that he's basically saying when you do this with electrons and photons, they arrive in units like a bullet. But they make a pattern like a wave. They make the graph like a wave. That's how they're doing both things. That had never been totally clear to me before.
Yeah, it's like a combination of both.
Yeah.
Yeah, both graphs.
Yeah.
Isn't that right?
No, it's not both graphs. It's that they arrive like they're singular lumps, unlike a wave, which is a wave is basically a wave doesn't have a
lump, yeah.
Yeah. So they arrive in lumps, like a bullet, but they make a graph like a wave, which is why it's both things.
That is not what I got from that.
Oh, really? Well, maybe I completely misunderstood it.
I thought at the end, but see, I was listening to it. You were looking at all the diagrams and stuff. So you're probably right. I thought that the result was the combination of the two different curves on the graph.
Yeah, there's probably that too. I mean, he's got a table here where he shows bullets come in lumps. Measure is probability of arrival, and there's no interference. Waves can have any size, so they don't come in lumps. They measure what you're measuring is the intensity of the waves, and this shows interference. Electrons and photons come in lumps, but they show interference, and you're measuring the probability of their arrival. So you see that the what's being combined here.
Yeah, so in the lumps, see, it's like this is equal to N1 plus N2. Now we're getting into the weeds of this stuff that
right.
like, doesn't make any sense. But
this is the same as this in terms of the graph. What's different is what I'm saying. The electrons and photons, they show up in lumps, but they read on the graph like a wave.
Yeah, okay.
That's I'm pretty sure that's what he was trying to get at.
Okay. Yeah, fair enough. I believe you. I like I said, I wasn't looking at the graphs and carefully reading. I'm listening to it while I was at work.
Yeah.
So,
But that was really cool, and I was like, oh, okay, I see what he's saying here. That a wave, something with that shows up on the when you graph it out, shows all the interference stuff and the basically the detection like a wave would, which it gives you a specific kind of curve that isn't the same as something that's coming in lumps. And yet it comes in lumps.
yeah. And so
This
they're
is
like,
why
which
he's-
slit did it go through?
Right, yeah. This is why he's saying you can't imagine how it's doing both of those things at the same time.
Yeah.
But it does those things at the same time. It shows up in discrete units and yet acts like a wave.
Yeah, that's weird.
Until you try to figure out, until you get curious and say, well, what is actually happening here? And then you start shining light at it to see what's going on. And then it stops acting like a wave and starts acting just like a regular bullet.
Only lumps.
Yeah.
Yeah. So weird.
So that's the double slit experiment. What time are we at? Is it another break?
Yeah.
Or are
I
we...
mean, we're going to have to do a short segment here.
Oh, okay.
We don't have to do it here, but we could do it at the end.
Yeah, let's do it here, I guess. Let's just stop here, and then I can finish off the chapter, and we can discuss it at the end.
All right.
On the next segment.
Well, we'll be right back then.
All right, yeah.
Now, you might think that if you were clever enough, you could argue that they have some way of going around through the holes back and forth, and they do something complicated, or it splits in half and goes through the two holes, and so forth, in order to explain this phenomenon. But nobody, however, has succeeded to get an explanation of this that's satisfactory, because the mathematics in the end is so very simple, the curve is so very simple. I will summarize then by saying that electrons arrive in lumps, like particles. But the probability of arrival of these lumps is determined like the intensity of waves would be. And it is in this sense that the electron behaves, as you might say, sometimes like a particle and sometimes like a wave. It behaves in these two different ways at the same time.
The Snake Bros Institute for Advanced Particle Studies, where we have no idea what's going on, and I am not asking.
You're not allowed to ask.
I am not asking in an angry manner. Why do they act that way? But yes, this is the final segment here.
Yep.
What else we got?
Probability and uncertainty. So you got to hear there during the break part of Feynman's discussion of the double slit
experiment.
double slit experiment. It was like really where he's trying to explain how they act in both ways. So he also says, I am not able here to discuss a large number of different ways which you might suggest to find out which hole the electron goes through. Like he's anticipating the students all coming up with ideas in their head. You could actually see this throughout the description of the experiment. He kept saying like, yeah, I know. You're all probably coming up with ideas right now of how you could do this. And trust me, we've tried them. He says, it always turns out, however, that it is impossible to arrange the light in any way so that you can tell through which hole the thing is going without disturbing the pattern of arrival of the electrons, without destroying the interference. Not only light, but anything else, whatever you use. In principle, it is impossible to do it. You can, if you want, invent many ways to tell which hole the electron is going through, and then it turns out that it is going through one or the other. But if you try to make that instrument so that at the same time it does not disturb the motion of the electron, then what happens is you can no longer tell which hole it goes through, and you get the complicated result again.
That's what I think. Yeah, that's what I would think of as like when you look, it shows up in lumps. When you don't look, it shows up as a wave. Basically, is what it is like, right? Are you thinking it's more is something else?
Maybe you're right. I really got the impression that it's always that's why he's saying click, click, click. It doesn't matter how many holes you have open. it's showing up as a discrete lump. And if you turn the